All right, let's get into it. We're always hearing about neural networks, AI, deep learning, but what does it all actually mean? How does a computer look at a bunch of pixels and somehow understand what it's seeing? Well, today, we're going to pull one apart piece by piece and see how it really works. It really all boils down to a question just like this one. If you try to write a normal computer program to find a cat, you'd be stuck writing endless if-then rules about whiskers and pointy ears. It'd be a nightmare. A neural network, though, it does something totally different. It learns. The real question is, how?
The secret here, the big reveal, is that this unbelievably complex system is made from one, single, really simple part that just gets repeated over and over. So rather than me just telling you about it, let's actually build one, right here, right now, from the ground up.
And that fundamental piece, that single Lego brick for the entire castle, is the neuron. This is the heart of the whole operation. If you get this, you're going to get everything else that follows. So what does a neuron do? At its core, its job is shockingly simple. It doesn't think. It's not pondering the nature of a cat. It's just a tiny calculator that does two little bits of math, one after the other. Let's break those two steps down. Okay, step one. The neuron looks at all the pixels in an image. Now, imagine it has two little dials it can turn. The first is a weight dial. It multiplies the pixel values by this weight to decide how important they are. The second is a bias dial, which it uses to kind of nudge the final result up or down. That's the linear calculation. Then, for step two, it takes that number and runs it through something called an activation function, which basically just squishes the result so it's always a value between 0 and 1. So if we're building a cat detector, a 0.9 just means I'm 90% sure this is a cat. And that's it. That's all a single neuron does. So that's great for a simple yes or no question, like, is it a cat? But obviously we want to do more than that. What if we need to spot a bunch of different things? How do we scale this up? So now, this is our new goal. We're not just asking one question anymore. We're asking three completely different questions about the same picture. And our little one neuron setup just isn't gonna cut it.
And honestly, the solution is just as simple and elegant as you'd hope. We just add more neurons. We'll make a little group or a layer of three of them. The first neuron's entire job is to look for cats. The second one only looks for lions, and the third is our iguana specialist. Now, the really important part here is that, at this point, they are completely independent. They don't talk to each other at all.
Now, that independence is useful, but it also creates a big problem in certain situations. What happens when we need the network to stop hedging its bets and make one single confident choice? We gotta force these neurons to cooperate. Let's just add one simple rule to the game. Let's say we know for a fact that every photo has either a cat or a lion or an iguana in it, but never more than one. How does that change what we need from our network? This shows the problem perfectly. On the left, with our independent neurons, you could feed it a picture of a lion, and the cat neuron might scream 90% sure it's a cat, and the lion neuron says 85% sure it's a lion. That's confusing. What we actually want is the behavior on the right, where they're forced to work together and spread their confidence out. The total probability has to add up to 100%, which forces a much clearer single choice. And the magic tool that does this is a different kind of activation function called softmax. So think of it like this. The old function sigmoid lets every neuron vote for itself. Softmax makes them all get in a room together, look at each other's scores, and then release a single unified probability that adds up to 100%. It forces them to work as a team and reach a consensus. Okay, so we've built a single, really smart layer of neurons. But the real power, the reason AI has exploded, comes from what happens when you stack these layers, one on top of the other. This is what we mean when we say a deep neural network. So any layer we sandwich in between our first input and our final output is called a hidden layer. And it's called hidden because we don't really tell it what to do. Its entire job is to look at the information it gets from the layer before it and just find useful patterns. It teaches itself to find abstract features. So what does that actually look like? Well, the very first hidden layer, it's connected directly to the image. It doesn't see a cat. All it sees are raw pixels. So it learns the simplest thing it possibly can. Basic things like horizontal lines, vertical lines, maybe some simple gradients of color, just edges. Now, the second layer, it never sees the pixels. All it sees is the output from that first layer. So it sees a bunch of edges. And its job is to figure out how to combine those simple edges into more complex shapes. It might learn that putting a few curves together in a certain way looks like an eye, or that a couple of diagonal lines makes a pointy ear. And then finally, our last layer sees the output from layer 2. It sees a collection of shapes: eyes, ears, a nose, whiskers. And it learns that when those specific features are all present together, well, that's a cat. It's this beautiful hierarchy of understanding, going from the incredibly simple to the incredibly complex. And that right there is the power of deep learning. It really all boils down to this one idea from the folks at Stanford. The deeper you go, the more complex information the neurons are able to understand. Every layer adds a new level of abstraction. So we've designed the architecture, we've built the structure, but right now it's still just a collection of random dials. It's dumb. So now for the most important part, how does it actually get smart? How does it learn? Well, the learning process is this really elegant three-step loop. First, the network makes a guess. You show it a picture of a cat, it runs all the numbers and spits out an answer. That's called forward propagation. Second, you measure how wrong it was. You compare its guess, the right answer, cat, and you calculate an error score. And third, this is the magic part. It corrects the mistake. It uses that error score and works its way backward through the entire network, a process called backpropagation. And it just slightly tweaks every single one of those weight and bias styles to try and make the error a little bit smaller next time. And that's it. That's the whole secret. Learning for a neural network is just this simple loop. Guess, check how wrong you are, and make a tiny correction. Do that millions or even billions of times with tons of examples, and the network slowly but surely gets really, really good. And this also explains why deep learning is happening now. This guess and correct cycle needs two things in absolutely massive quantities. First, tons of labeled data to learn from, and second, an incredible amount of computing power, which is where things like GPUs come in to run through those billions of cycles. Which leaves us with one final and kind of mind-bending question. Remember, we only ever tell the network if its final guess was right or wrong. We never tell those hidden layers in the middle to look for edges or shapes. The fact that they figure that out all on their own is an emergent property, and it gets at one of the deepest, most fascinating mysteries in all of AI.